Welcome everyone back to the CPAR weekly seminar. I want to take a moment to thank Dorsa and Lauren for actually organizing and putting this all together. So thank you both. All of your team. And actually I want to say that one thing that's been really making this possible this semester, especially bringing in our super esteemed our speakers, such as the one we have today, is that we're collaborating. This is a CPAR and DREAM seminar together, and it's been a really wonderful opportunity to collaborate. And we actually are particularly lucky today because we have our dean and a leader of the DREAMS group, Shankar Sastry, who is perfectly in a perfect position to do the introduction today. Because, as I just learned, our speaker was on his thesis committee. So with that,
most of all, I want to tell you what a treat it is that you have Lotfi as your speaker today. Lotfi has an amazing set of accomplishments, and I won't go through all of them, but let me just have a more personal introduction. I'm actually Lotfi's intellectual grandson. And he was on my committee. He was actually the chair of my committee, but also, he was one of his PhD students was Praveen Varaya, who was one of my advisors. But, Lotfi has been pretty instrumental in the department and in the college. And, for many, many things. When I first came to Berkeley, Corey had only 4 floors, and there was no soda. Actually, the computer science division was on the 5th floor of Evans. And my first memories of really walking into this, I really let him speak, I'll get off in 30 seconds, this is really about his talk. But Lotfi used to maintain a push-pin board on the 4th floor called Open Problems in Systems Theory. And it said that anybody was welcome to post a problem, but solutions needed to be turned in to Lotfi for his... And just another thing, Lotfi is such a distinguished professor. He is the professor in Berkeley with the highest number of honorary PhDs. And I will kid you not, he has more than 30 honorary doctorates. And I'll tell you a little story. We had a birthday party for Lotfi in the faculty club a few years ago. And, it was a birthday party that was going along. And then halfway through this, we were in the faculty club, and groups of people from several universities, and they were rectors, who came up to me and said, they have something very special to do. And on that one evening, they had come with the academic robes to be, or to be, because if they could not get Lotfi to come to their home institution to award the honorary doctorate, they actually came to the faculty club to perform the investiture. I don't know if you remember all this, Lotfi. I'm sure you do. I know you're deadpan about all of this. But, it's really a treat. And you can see that, there is a lot to do. So welcome. Thank you very much, and thank you for everything you've done. Please.
Sabina,
Please.
can you turn me around? Thank you. Thank you very much. Well, you see me in a wheelchair. I'm in a wheelchair not because of some medical problem. Well, there is a medical problem. I fell on my back in the parking lot of Fat Apple restaurant in El Cerrito, and I hurt my back. No fractures, but sufficient injury to keep me in the wheelchair now for a couple of months. I've been in the wheelchair, and it's not really pleasant. I must tell you that, but what can I do? This is what happens in life. So it's my great pleasure to be here today, and I want to express my deep appreciation to Shankar for coming to this lecture. And I could spent a lot of time talking about Shankar's accomplishments as scientist, as administrator, and as intellectual leader. But I won't do so. I won't do so. So, my assistant is Sabina. She's a lineage scholar from Azerbaijan, where I was born. What you see here is a medal called Medal of Friendship from Azerbaijan. So I'm considered to be their native son in Azerbaijan. I have my phone here to tell me what the time is. So, my voice is a little bit, I have to apologize for many things. Another thing is this, that I have problems with dry mouth. And when my mouth is dry, it becomes a little bit difficult to understand me. So please accept my apology. Please accept my apology. So, thank you so much. There is a microphone here somewhere.
There is a microphone here.
Yeah, put it in the jacket.
This one? Oh, this one? Or this a small one?
Whatever it
Can you speak now?
It is sufficiently loud at this point.
That's better. Yeah, that's
Okay,
microphone.
Sabina,
Yeah.
could you hold this
Huh?
and check at the time, okay?
Yeah, I will tell you.
Okay. So, I personally feel honored by having Shankar here. Shankar is a superior intellect. That's how I call him. Superior intellect. But he's also extremely talented organizer and administrative leader, intellectual leader. So, anyway, let me go on to my presentation. So my lecture is concerned with stratification. Now, what is stratification? Stratification is when you take information and you stratify it. So you have layers. Familiar examples are telephone directories and catalogues and things of this kind. The information is stratified. And so my point here is stratification is something that has many applications, particularly in the realm of robotics and optimal control and planning, and more generally in situations in which you have what they call a target set, some sort of a goal that you want to reach. So what you do then is you stratify information to reach that goal. For example, you want to find somebody's telephone numbers. So what you do then is you, thank you so much. I hope that will improve a little bit my voice. So, Sabina, could you change it?
To the first one. Abstract.
Yes. So for short, what I'm going to talk about we call CST. ST stands for stratification. Okay, so let's take a closer look at it next. Okay. So what we have is this: either the information is stratified, or else you organize it in that way, it's stratified. Now, as I said, stratification has many, let's say, incarnations. For example, like an academic institution, you have stratified classes, and years of study, first year, second year, third year, fourth year, you stratify them. You stratify organizations, and you stratify actually many things. Okay, next. Okay. So, the principal obligations are those in which you have some sort of a goal. I call it target set, and you want to reach that goal. And in robotics, that is usually the case. There's something you want to grab or something to move, whatever, but you have some goal. Or you want to park a car, that's a goal. Now the question is, how do you do that? So what we're going to talk about is some sort of a general approach to problems. We have a goal, and you want to reach that goal. So this is roughly what we're going to talk about. Next. Okay, next. Okay, next. Now you see that I have too many slides, so I'm going to skip many slides in my presentation to fit the time that I have available for my presentation. Next. Okay. Now an interesting question is this. You take the human brain. Does the human brain use stratification? It's quite possible that the human brain uses stratification. And that is why, for humans, you can ask a question and a human can answer that question very quickly. And just as in the case of dictionary, you can find the meaning of a word quickly because you stratify information. So that's the point. Okay, next. So you stratify, and then different strata that are used to store information about some particular concept. For example, you have chair, the concept of chair, and then you have office chair, lounge chair, and so forth. So each of these versions of the concept of chair then is stored in some strata. Okay, next. Okay, next. Okay, so what we're going to do, we're going to use a model. That model will be a finite state model. Finite state model. A finite state model is a discrete time, discrete state system, which has a finite number of states. I think that the concept of finite state model is very important. And what I think historically, what happened is that in engineering and many other fields, you study differential equations, but actually you should study first FSM, finite state model. You should study that first, because that's easier to understand and easier to program. But for historical reasons, we start with differential equations. So in this model over here, we assume that we have a finite state model. Okay, next. Next. Okay, so the concept of reachability is very important. Now, let me give you just a few examples. Assume that FSM in this case is a patient in a hospital. So the goal is to cure the patient. So that's the goal. And so the goal is reached where the state of the patient is cured. That's the way we look at it. Next. And usually we want to reach the goal in the minimum number of steps. We want to reach it quickly, not take a long time. So what we're going to use is what I call incremental enlargement principle. And you see the simple thing, and I think it would be worthwhile to try to park a car using this incremental enlargement principle. Automate parking a car. Toyota has a system for parking a car, but this would be different. Next. Okay. Next. So many applications: optimal control, pursuit, search, and so forth. Next. So our approach is systems-oriented rather than logic-oriented. Next. Next. So what is this here? See, it is a system of computation in which the objects of computation are strata of data. So if you say, find the telephone number of so-and-so, then it's a system of computation. You find the telephone number, but the information is stratified. That's what happens. Next. Okay. Usually we have this as a state space, and usually the target set is somewhere. Let's say here, this target set. So you have this strata, and this is the nested strata. Nested meaning that one contains the other one, like this. And here is the target set. And so a simple example, as I mentioned earlier, is telephone directory. What I could do, I could have a box, and in that box I have a bunch of cards. Each card has the name of a person, and that person's telephone number. Now, to find the telephone number of a person would be difficult. It's easy to find the telephone number if you have a telephone directory, which is stratified. So what happens is this. So you try, given a starting point, you can try to come up with a way of going to the target. But in the approach I'm going to discuss, you're going from one stratum to another stratum. So it's easy to go from one stratum to another stratum. And this is basically what's done in dynamic programming, except that CSC is much simpler to understand than dynamic programming. But the basic idea is that you go from one stratum to another stratum. Or in this building you want a room. You go from strata are the floors of the building. So you go from one floor to another floor. And now the question is, how can you get to the room that you want as soon as possible? So you go from one floor to another floor, and so forth. This is roughly what's involved in this kind of situation. Next. So we have nested or we have stacked. Stacked is like telephone directory, and nested would be like the figure that was shown there. Next. Okay, next. Next. So we also have the concept of stratified count. How many students are in the college engineering at Berkeley? Well, there's a number, but you can stratify it. We have first year, second year, third year, and fourth year. And then you say, in this stratum, you have so many students, so many undergraduates, so many graduates, so many PhD, and so forth. And you can see that this sort of organization helps to find some particular person or decide what to do in some particular situation. Next. Okay. Now, stratified count. In some situations, well, I referred to that a moment ago. How many students are in the college of engineering? So stratified. So you have so many undergraduates, so many graduates. So this would be called stratified count. And stratified count, I think, is very useful when you have a poll. So how many people are going to vote for some particular proposition? To stratify. You say you have catalogues, you have minorities, you have business people, and so forth. You stratify. And then you say a certain percentage of business people are going to vote, a certain percentage of Catholics are going to vote, a certain perception of black people are going to vote. And you can see why for a politician it is very useful to have stratified count. I will just the count. Okay, next.
Professor, 30 minutes left. 30 минут осталось.
Next. 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 Okay. So we're going to talk about FSM. So FSM then. Next. Next. Okay. So we have various concepts. Next. So we have input sequence, and that input sequence changes the state of the system. Next. Okay. 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 So, okay, next. I'm sorry, I'm going to skip many slides. Okay. Now you can also stratify like this. So you can have a floor plan, and you want a vehicle to go from one place to another place. So you stratify it like this, and you go from one place to another place. So you can stratify also, for example, the medical state of a patient. You can stratify that, and you have temperature, you have blood pressure, and various other things. And these parts of the state of the system. Next. Okay. Okay. So we have state variables. State variables are variables whose values define the state of the system. Next. So this is the set of state variables. And this set state variables have to be given by the system designer. So you have to park a car. So the system designer has to tell what are the state variables, its location, its orientation, and so forth. And when you instantiate the state variables, then you have the state of the system. Next. Okay, next. Well, this is the example of a patient, temperature, blood pressure, and so forth. Next. Now there there's a property which is an important property, separation property. A state separates the future from the past. So if you have a state of a system, then at time t0, then from time t0 on, the behavior is determined only by the future, not by the past. So it's important that the state have this property. So when you define the state of a system, it's essential that the states have this separation property. Okay. Next. Okay, next. Okay, some basic concept. Next. 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 So, I've always been interested in sort of foundations on system theory. So the concept of state plays a very important role in system theory, but in also in many other fields. Okay, next. Okay, so we have input-output pairs. So you apply an input in a certain state, and then you observe the output. So you get an input-output pair. So in the book that Charlie Dussault and I wrote back in '63, state-space approach, this system is defined as a collection of input-output pairs. That is the point of view that's used in that book. And so if you have finite state systems, then you have sequences. And so input-output sequence, and they come in pairs. Input sequence, output sequence. So that's the system. Next. Okay. Next. The input and output sequence have the same length. Next. So they form a bundle. Now this is a tag. The tag is a state. So you apply input and you observe the output. When the system is a certain state, and that's the state, and you get a connection of input-output pairs. So that becomes a bundle. So if you start with input-output pairs, then you bundle them. And once you bundle them, then it becomes easier to analyze the system. Next. So what is fundamental is the state transition function. It tells you that if you're in a certain state at time t, and you apply certain input, then you move to the next state, st plus 1. St plus 1. This is state transition function. Now this state transition function can be represented in different ways. Next. Next. Okay. So this state transition, and this is the output. The output is a function of the state and the input. Now, when we deal with differential equations, so we have x that is f of x and u. So differential equation is sort of could be viewed as a special case of it. This is a little bit more general. So if you discretize this, if you discretize differential equation, then you come up for a state. It's an interesting question. If you start with the system, which is described by differential equation, how do you come up with a finite state approximation to the system? It's not a trivial problem. Next. Next. So this is a tabular representation. If you are in this state and you apply this input, this is length 1, then there is output. So this will be a tabular representation of the system. But you can also have diagrammatic representation. Next. So if you are in this state and you apply some input, you work here. And if you are in this state and apply input, you work here. This will become state diagram. The state diagram then defines the final state system. And state diagram is rather convenient to work with. And it's all kinds of problems that can be formulated in terms of state diagrams. Next. So, the target set is a set of states in a state diagram. That's the target set. Let's go back one. So, we say that this is the target state or target set. So given any point here, state you want to come up. So this is the goal. Against the goal, this is the target state. For example, in the case of parking, this is the parking spot, and you have a vehicle, so you want to move the vehicle through a succession of states to this final state, and the final state is the target state. Next. Now the second concept here. If you are the concept predecessor and success, if you have a state, then there's a state from which this state came from. That's called predecessor, and this will be successor. If you apply an input, you go to another state, and that will be the successor state. So given state diagram, you can easily figure out what are the predecessor states and the successor states of any given state. Okay, next. So a state can be both a successor state and a predecessor state. Now, interestingly enough, when you talk about differential equations, these concepts do not appear, but if you talk about FSM, then they do appear, because the predecessor state, successor state. Next. Okay, next. So we have a path. Next. A path is a sequence of links. So in the state diagram, we have links from one state to another state. And if you take a path, then there will be a trajectory from one state to another state. Next. So again, they're talking about the patient in a hospital, and they have finite number of state variables: temperature, blood count, hemoglobin level, and various other things. And so we want to go from initial state, which is the state that the patient has when that patient to a final state, which is cured. Blood pressure is normal, temperature is normal, various other things are normal. Then we say that the patient is cured. Next. So the main thing is how do you go from one state to another state. Next. Okay. Next. Okay. This is patient again. Next. Okay, next. Okay. Now, so the target set is defined by what I call defining proposition. The defining proposition is the patient is cured. That is the proposition which defines the target set. So that's what we have. Okay. So remember that our main concern here is how to go from an initial state to the target state. In the case of parking of the car, we have a target set. Notice that there are more than one target state. We have a whole bunch because the final position is not specified. You need to have final position. There's a whole bunch of them, and that's what we call the target set. So given the initial position of the car, how do you apply a sequence of inputs that will take the car into the parking spot? That's the problem. Okay, next. 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 Okay. Next. So we stratify the state space, and we have strata from which the target set can be reached in n steps, n-1 steps, and so forth. So stratification will be concerned with the number of steps that are needed to take the initial state into the target set. Okay, next. Next. Okay. Here you have reachability relation. If you go from one state to another state, then that state is reachable from the initial state. If you take a patient and take the patient, have certain treatments, then you change the state of the patient. Again, the question is, can you change the state of the patient so that from having high blood pressure, the patient will have normal blood pressure? So this is what we're interested in. Now, there are a bunch of slides that are concerned with this reachability relation, but I'm going to skip them because they're not crucial to what I'm going to talk about next. Okay, next. Next. Notice that in city planning, we frequently stratify the area around the downtown of a city is the target set, and then you have belts, and these belts are strata. And if you want to go downtown, then you move from one belt to another belt. That's how the transportation system is organized in many systems, states, many cities. Next. Okay, next. Okay. In some instances, the target set is fuzzy, that is a matter of degree. If you are reached, downtown is fuzzy. It's not something that is sharply defined. The boundary of downtown is a fuzzy boundary. So if I want to reach for downtown, there will be degree to which you reach downtown. If you are Union Square, San Francisco, then you have reached downtown to degree 1. But if you have some other spots, then you may have reached to a degree that's less than 1. Okay, next. So what we're going to do is this. We're going to lower our objective. We're going to say that it will be good enough to reach not the target set, but something that is close to the target set. So that's good enough. So we add to the target set states which are close to the target set. Okay. And that is equivalent to enlarging the target set. Next. So, incremental enlargement principle refers to a situation in which the target set is enlarged incrementally. Next. We also have multi-objective optimization, more than one objective. So you want to reach a hotel in downtown, but you need more than one hotel, so you have different objectives. So how do you reach that? Now, the process was described in a paper by Bell and myself is that you introduce sets, fatigue sets, and then you form the intersection of the fatigue sets. Next. So we're going to use this. Next. So if we have, let's say, two target sets, then we say that we can replace the two target sets with the intersection or conjunction. That means we are reaching both this and that. So then we're saying that if you have more than one objective, then form the conjunction of the objective, or if we form the intersection of the objective. Next.
10 minutes.
Okay. Next. Next. Okay. Next. Okay. So now we want to go to that principle. Next. So this is the intersection of target sets. This is what we do. Next. 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 So we can combine these sets through conjunction. Next. Conjunction or intersection. Next. This is intersection. Next. Intersection. So in this paper that I referred to, the simple idea that is introduced is this. If you have a multiplicity of constraints and target states, then form the conjunction. The word conjunction means and, because you want to reach this, I want to reach that, and so forth. So you form the conjunction of your goals. Next. Next. So by forming conjunction, then we replace multiplicity of objectives with a single objection, which is the conjunction of the other objective. Next. Okay. Next. Okay. Next. So we have this property. If S is the set of states from which you can reach a target set in n steps, then Sn minus 1 is a subset of Sn, because if you can reach it in n minus 1 steps, then you can certainly reach it in n steps. Next. Okay. Next. Next. So remember, our main thing is stratification. How do you stratify? That's the objective. So, okay. So what we do is this. Next. We take the initial target set. Next. Next. You can also stratify functions, and that's very useful in certain computation for stratified functions. Okay, next. So we have horizontal stratification and vertical stratification. Next. Okay. Then you work with numbers and Z numbers. Z number is a pair of complex numbers. Next. Next. Okay. So what we do is this. We say that we want to, if we are satisfied with getting to something which is close to a target set. So what we do then, we add states which are close to a target set. And we do that next. So that's the principle. We do that through next. 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 By adding to Sn predecessors of Sn, because predecessors are one step away from Sn. So we add states which are near, meaning one step away, and one step away is predecessor. Okay. Next. Next. So if this is a target, we add one step away, two step away, three step away. So incremental is that we add just a little bit to the target set, and we advance. And as we advance, we stratify the space. We stratify the space. Next. And we have annotation. With each state we associate annotation. Annotation is the sequence which takes that state into the target set. Next. Okay, next. Next. Okay, next. So, then we do this. We're saying that Sn plus 1 is Sn next. We're saying Sn plus 1 is Sn plus predecessors of Sn. And that is a fundamental thing here, this equation. Sn plus 1 is Sn plus predecessor. And we can find predecessor from state and feature function. So that given the target set, we advance. Next. We advance incrementally and enlarging the target set. That's what's called incremental enlargement. Now, for some parking problem, we incrementally enlarge the target set. The target set is the spot where we want to park the car, but we enlarge it incrementally. And as we enlarge it, then we stratify the state space. And then we can park the car by moving from one stratum to another stratum. Next. Okay. So we can easily stratify the state space by using that equation. Sn plus 1 is Sn plus predecessor of it. Next. Next. So this is the target set. And then we enlarge it a little bit. Predecessors of the target is 3. 3 and 6 and 2. So from 3, we go to 3 and 6, we enlarge it. And we take this, and we enlarge this, and so on. Next. So this is the process of enlargement of the target set. Now notice that if we solve differential equations, then it will be difficult to do that. With a finite state machine, predecessors are easily defined so that you can find predecessors very easily, and we simply add it, and then we stratify the whole thing next. So this is a recursive thing which tells you how to stratify the space. Okay, next. So we have incremental enlargement equation. Next. One is for T and the other one for S. Remember that S stands for stratum and T stands for target. So we can enlarge target shape and we can enlarge stratum. Next. Okay. So I think it will be quite interesting and challenging to take this and apply it to the problem of parking a car. Because in case parking a car is associated with three state variables: location of the vehicle and orientation, three state variables. And so initially we start with certain location, orientation. And then we have parking spot. We enlarge the parking spot. And as we enlarge the spot, we stratify the whole space. And once we stratify the whole space, then we can move from one stratum to another stratum. Next. So this is the state space. So we can stratify the state space. Next. Okay. I think that I'll stop at this point and summarize. Some of you may be somewhat unfamiliar with finite state machines, but I want to emphasize this: the finite state machines are much easier to deal with than differential equations. But dynamic programming basically involves the same thing. You have a final thing, and then you step back. You step back, and then you have a simple problem. You want to reach the final thing in one step. And then you step back, you step back, and you step back, and so forth. The back propagation machine or algorithm involves the same thing. Stepping back, that's what we call back propagation. So let me then just summarize what is the gist of this thing. He said you're going to work not with differential equations, but with finite state machine. And again, the finite state machine proximity is number of steps, one step, two steps. And then they say that if you find predecessor, that's one step away, and then you move one step away from that. And using this recursive thing, recursive in the sense of Sn plus 1 is defined in terms of Sn. Then we can stratify the whole space and solve the problem. So that's really basically what is the gist of this approach. So notice that in the title of the talk, I said stratification, target set reachability, and the incremental enlargement principle. So the question is, okay, but how do we stratify? At that point, we pull out the incremental enlargement principle and we stratify, and that will then solve the problem. And I think it will be interesting to apply it to the parking problem. And or to other things, or to search. You want to find something. So again, you stratify the search space, and then you move from one stratum to another stratum, where they search from a sunken ship or sunken whatever. That's the approach that we use, stratification. Okay, so I think I'll stop at this point. And if you have any questions, I will try to answer them to the best of my ability.
Okay.
I have a hearing aid, so please speak loud. I may have some difficulty understanding what you're saying. Yes, go ahead. Sabina, perhaps you could.
Lotfi, most of our junior faculty
Yes.
get tired at about 40 minutes in, but you have gone a tremendous distance here. We're so impressed that you keep. I actually feel you could have gone on for another hour on this subject. Your stamina is impressive. Thank you.
Thank you.
One question I have for you is:
We need younger people like.
are you assuming for now in this model that the transitions are deterministic? Do you assume that the transitions are deterministic between states?
I do say in the text of this thing, there could be probabilistic. In which case, reachability relation is a probability distribution. What's the probability of reaching that state or this state? In the case of the patient, it is probabilistic. You cannot be sure that some particular treatment will take the patient from one state to another state. You're saying it's likely that if you give certain things, then the blood pressure will go down, but yet it cannot be absolutely sure.
Because a related question is to what degree a fuzzy model could be developed for that probabilistic transitions?
Pardon me?
A fuzzy model of the transitions. Is there an equivalent model?
Well, in the case of fundamental, you move from one state, not deterministically to another state, but things which are in the vicinity of that state.
But you don't have a sense of being in partially another state or in two states, or multiple states possibly?
Yes.
That could be. Okay.
Yes.
Gets into the realm of like almost quantum type of a model. Where you have
Now, let us say this, that there is a paper that I wrote that's available in case you would like to have a paper or the slides. Send me an email message and I'll be pleased to send it to you.
Okay, Lotfi, we'll post the slides on the website if it's okay with you.
Okay, fine.
Great. And the paper reference too?
Thank you.
Very good. Awesome. Okay, well thank you so much. We really appreciate it.
I have to thank you for giving me an opportunity to discuss this particular technique. I really feel that there is something that is practicable, so it's not just something theoretical, it's something that you can take and program it and come up with some interesting solutions in the realm of robotics, parking, or curing the patient, or many other things. And I think that now in the case of financial systems, you do have transition from one state to another state. If you have a patient, it would not be so difficult to define it in terms of finite state model. Very difficult in terms of differential equation. I was brought up on differential equation, but at some point I switched to finite state systems. And I've been of the opinion ever since that this is what should be taught first. And so I was teaching courses in ECS. I taught a course on finite state systems, and that course came before a course on differential equation. I feel, and I'm repeating myself, I feel that it's really very useful in terms of your capability of solving various problems to become conversant with finite system theory.
Thank you, Rob. Appreciate it.